I'm very pleased to be here and to speak with you all this evening, albeit via the power of the internet. So yeah, thank you to Edinburgh Building Retrofit Improvement Collective for firstly organising and hosting an event like this, because more of this is certainly sorely needed. But also thank you to them for inviting me to speak with you all this evening. They have done an amazing job at organising all this and making my contribution really streamlined. And thanks to all of you for taking time out of your schedules to be here. So I want to start off with why should you be listening to me? Now, this isn't some attempt for me to promote building research solutions by company. Rather, these next few slides are here to qualify me to speak on this topic and to reassure you that you've made a good choice by choosing to be here this evening. So building research solutions, or BRS as we're known, is effectively broken into two parts. So my business partner, Ruth, leads on the whole life cycle and embodied energy and carbon R&D side, research and development side of the company, and I lead on the operational energy and carbon R&D side of the company, which simply means that I lead our projects that focus on energy use in a building when that building is being occupied, and Ruth leads on projects that focus on the energy and carbon required to create a material, transport that material to a site, construct with that material, and then build a new building or do a retrofit project. Then we would investigate things like end-of-life scenarios for those materials after they've reached the end of their life, which also includes things like circular economy. Both of us effectively spun out of Edinburgh Napier University's Institute for Sustainable Construction in 2020. Ruth left the Resource Efficient Built Environment Lab Research Centre, and I left the Scottish Energy Centre. And since then, I've been appointed as Regional Chair for the Chartered Institute for Architectural Technologists in the Scotland East region. So both of our academic research centres were applied science centres, which means that all the projects that we worked on were industry-led and industry-focused. Now, we at BRS continue to support the people and organisations that are effectively supporting you as homeowners or as occupants. So for retrofit, our clients are typically architectural designers, surveyors, retrofit installers, material manufacturers, housing associations, and housing cooperatives, etc. So whilst we do work with all different types of buildings and projects and methods of construction, we do have a very long history with the existing Scottish buildings, specifically the traditional / historic / pre-1919 variety. So over the last 13 years, I've personally crawled through attic spaces and crawled over the top of roofs, through basements in the Solum area, to add every type of sensor to every conceivable location, all in the name of science, to better evolve our understanding of building physics for these particular archetypes. So this is that sort of activity is what used to be called retrofit building performance assessment and evaluation, which is often now referred to as retrofit assessment and retrofit evaluation. But do be careful with those newer terms, because they are grossly slimmed down versions of a full building performance evaluation, which I'm going to talk about tonight, the fuller version. So we have used lots of different hardware, including loggers and sensors for temperature, relative humidity, moisture content, air movement, heat flow, infrared imaging devices, low pressure and high pressure air permeability apparatus, 3D LiDAR scanning, and lots of other stuff. And we have assessed and evaluated the pre and post retrofit agrothermal performance of buildings right across Scotland, from Uist down to Rothsay, from Cooper to Edinburgh, and all along Scotland's central belt. Now, back then, most of our work was funded by Historic Scotland, and as such, I've either directly published or provided the scientific data and results for the publication of what was the first 10 refurbishment case studies, and then 4 technical papers on retrofit methods for this archetype. All that early work that we delivered to Historic Scotland, now called Historic Environment Scotland, myself and my colleagues at the Scottish Energy Centre at Napier there, we launched the retrofitscotland.org knowledge exchange portal, which we built alongside with Architecture Design Scotland, BRE Scotland, and Historic Environment Scotland. All of my research on retrofit methods was used to launch the first wave of case studies on that site. Now, sadly, that site did die around 2017, 2018, which is a shame, but a lot of the content that was on that site now lives in the archives of the HES website, and the link is on the screen there, which I'm sure EdinBRIC will share with you all. Last thing before I properly start the talk is I want to do a quick terminology check. So you're going to hear me say the word retrofit a lot, and this is what I mean whenever I say the word retrofit. So it's to add additional or replace existing materials and or technologies with ones which will improve the building's energy efficiency, and these relate to insulation materials and energy generation systems and can relate to those that conserve water. Now, words like renovate and refurbish, they do appear to be used interchangeably with the word retrofit, but those three words and these 5 R's, they do mean different things, but ultimately it doesn't matter what definition of word that you're using, as long as you know what I mean by whenever I say the word retrofit for the duration of this talk. Right, so now moving into the actual topic of the talk. So I want to cover 5 topics. First, the equilibrium and balancing of environments. So I want to start by taking a brief look at the fundamentals that govern building physics. Then move on to energy balancing, which is gains and losses. And here I want to do a quick breakdown on the types of thermal energy exchanges that are happening in our buildings with a very simple example. Then water transfer and ventilation. So here I'll explain how thermal energy relates to hygrothermal, which is the movement of both heat and water, and where ventilation plays in all of this. Then I'll move on to data capture to inform energy efficiency retrofits, and we'll look at the different hardware that can be used to monitor pre and post retrofit performance. And then we'll finish off with whole building energy efficiency retrofit measures. Now, for time's sake, this evening, I'm only going to cover thermal fabric retrofit measures, which is to say insulation materials. So I'm going to try and keep all of that to below an hour. So whilst I can and have spoken on this topic for hours and hours, what I'm about to say can be a lot to absorb, it can be a lot to decompress and consolidate to a point that makes sense to you all. So I want to leave a good amount of time for questions to have a little bit of feedback. Last thing before I start, I must say that I am about to cover a topic that people like myself have turned into 4-year university degree programs, and people, again, like myself, have turned into 3+ years of PhD level R&D on the topic. But I think that that Mick from Banzai said it best when he said that in the time available, we'll provide an overview of the technical fundamentals to help puzzle through the energy efficiency and building performance uncertainties without the scary math. There's a wee bit of math, but it's not that scary. So the takeaway messages for tonight will be: understand why energy efficiency is not as simple as blocking every draft and insulating everything. How to gather actionable information for making informed decisions. Understand when an obvious choice may benefit from careful consideration or require expert advice. And also the right type of questions to ask to your chosen retrofit professional. And finally, understanding when recommendations may be based on poor understanding or insufficient knowledge. Right, so let's kick off with the fundamentals of building physics. So I teach, and building physicists are taught, that the core of building physics is equilibrium. So quite simply, this means the equilibrium of environments. Now, within those environments, the conditions are in a constant state of flux. So there's a constant balancing between thermal energy, which we'll call heat, water vapor, and air movement. And we can think of these 3 conditions as defining our environments. So the external environment is in a constant state of flux because those three conditions are changing at various different rates and different speeds during the day and during the year. Then when we create a building, so by a building, I mean we construct a floor, walls, and roof, and we combine those together into a building, we are effectively partitioning and enveloping a volumetric part of the external environment into its own separate environment, almost like a microclimate. So if this building remains unconditioned, then the internal conditions will be very similar to, but will lag behind the actions of the conditions in the external environment. So this lag is usually in the range of a few minutes to a few hours, and the extremes typically aren't as high or as low in the internal environment as they will be externally. But the important thing to note here is that the internal and external environments are in close equilibrium, and this lag between the two happens because the walls, roof, and floor will act as the wind and precipitation barrier, thereby reducing the effects of those large swings in the internal conditions. Now, when we introduce people into our building, we create a need to further reduce these conditional swings in the internal environment, even further than what it would be if the building remained unconditioned. So we need to stabilize those internal conditions to create a more stable internal environment. So we artificially heat and we try to cool this volume to compensate for what is happening outside. So then we have now created an internal environment that is different to the external environment. It's very different to the external environment. So those walls and the roof and the floor, they now take on a new role within our building. They are the building's thermal envelope. That's the building's thermal envelope's job to manage the environmental differential between the internal and external conditions. Then as we subdivide the volume inside our envelope and expose it to various temperatures and concentrations of water vapor, we are effectively creating sub-environments. Now, when an environment is divided, which includes a physical division, like an internal wall or an internal floor, and also a conditional division, so for example, a bathroom and a bedroom will experience different levels of temperature and different levels of RH at different times. They then work to balance any variations in temperature and air movement and water vapor across those physical divisions, which are your internal walls and floors. So each of our sub-environments are now also in a constant state of flux. Each sub-environment inside the building is trying to balance the temperature, air movement, and water vapor across the indoor environment. And the whole internal environment is trying to balance with what is happening in the external environment. So it's up to our building's thermal envelope to buffer this balancing in a way that suits our agenda. And our agendas typically mean that we're trying to circulate foul or bad air from concentrations of human existence, which with fresh external air, which what we call maintaining respiratory comfort or good indoor air quality, reducing the amount of fuel that we're using to change the internal temperature from the external temperature to maintain thermal comfort, and prevent conditions for the germination of mycelium spores, which is to say surface condensation and mold growth. So this fundamental part of building physics, it is agnostic to any type of building. So the principles here apply to new build construction just as much as they apply to the retrofit of existing buildings. The main difference here is that for the purpose of this talk this evening, before you retrofit an existing building, its thermal envelope has been managing the internal conditions of the internal environment for the same way for the last 5, 10, 50, or 100 plus years. When you alter or add any material to that building's thermal envelope, you're fundamentally changing how that thermal envelope now manages and buffers the harmonization of the internal environment to the external environment. So with that covered, I now want to have a look at balancing across our building's thermal envelope. So we'll start by talking about energy, which refers to thermal energy. The first thing to note about thermal energy is it's a form of heat. And like all energy exchanges, when heat energy enters or leaves a system or a building in our example, it transfers through the line of least resistance. So it's often good to think of heat like electricity, and we know that electricity will jump around insulators to connect with other conductors, and heat, and in fact water vapor, behaves in a very similar manner. It will travel the line of least resistance. So balancing is looking from the perspective of reducing active heat generation, which is to say reducing the amount of heat generation from a boiler or a heater. With that in mind, balancing means to minimize the heat losses through the building's thermal envelope and maximize the heat gains. And this is known as passive heating. So if you're familiar or you've heard the term passive house or Retrofit, this balancing to minimize losses and maximize gains, it is the founding principle of passive house and Retrofit, but it is not exclusive to the passive house movement. It is in fact the basis of all building physics. So for heat loss, we can categorize these into three groups. We have planier, bridging, and ventilation. So planier heat loss is heat loss through the internal surface of the thermal envelope. So that means the temperature difference from inside to outside through your walls, your ceiling, your floor, closed windows and doors of our homes. Bridging heat loss is similar to planier, but bridging is the temperature differential through corners, joints, and junctions at the point where your planier elements change. So for example, it'll be a corner between a ceiling, a wall, or a joint where a wall turns into a window. Ventilation heat loss is most likely the one that we're all most familiar with because it's often referred to as a draft. And because of that, ventilation heat loss is often seen as being the bad guy, meaning that ventilation heat loss is almost always incorrectly considered as something that we must stop, rather than something that needs to be balanced to maintain adequate amount of air change rates to maintain good indoor air quality. But we'll come back to air movement in a few moments, and we'll talk about the difference between regulated and unregulated ventilation heat loss. So I wanted to have a cool little infographic here to kind of describe what I'm about to say, but sadly this matrix was the best way to articulate this next piece of information. So this slide and the next one, I've got something of like a cheat sheet on how to think about and consider these three heat loss pathways. So for planier is a function of the surface area in your home or building. And it's what the construction industry will call a U value or a thermal transmittance value. Now be careful with that terminology because I've seen websites, blogs and articles, even those from official construction companies, use the word thermal conductivity or use the word thermal resistance when they actually meant thermal transmittance. Now those three words are related, but they aren't interchangeable and they do mean different things. Bridging is a function of linear length. So that will be like the length for a junction between, say, your wall and your floor. This is often called thermal bypassing. And this has two metrics. One is called a psi value and the other is called a temperature factor. Importantly here, the temperature factor is an indication for the risk of surface condensation. And ventilation heat loss is a function of the home's internal volume. Now, this one has a whole host of different names. It's referred to in different ways and has different units of measure. But essentially, it's measured as either air change rates per hour or air permeability through your building's thermal envelope. On to the next part of this matrix, planier U values are calculated by designers or retrofit installers using software. Now, this, like almost all calculated values, they can be measured by building performance evaluation hardware, which we'll talk about very soon. The way to improve planier heat loss or reduce the U value is to add an insulation layer to that element. Now, we're going to talk about these insulation layers and where to add them in a few moments, but just simply for the purpose of this slide, adding an insulation layer would be like adding something like internal wall insulation or ceiling insulation or secondary glazing, for example. Bridging heat loss or psi values and temperature factors are calculated in pretty much the same way as U values. You have your retrofit professional using specific software. Now, temperature factors, but not the psi value, it can be measured just like U values, but it's measured using an IR camera, an infrared camera with surface temperature sensors. Now, the way to improve bridging heat loss is to ensure that the planar insulation overlaps between elements. So your internal wall insulation and your ceiling insulation, making sure they overlap as much as they can. Now, this is much easier said than done, which typically means that the bridging part of the heat loss trio is usually overlooked. But you should know that the bridging must at the very least be considered. So this is something you can raise with your chosen construction professional when the time comes to retrofit your home or building with thermal materials. And in flatted dwellings, flatted accommodation, this is usually the best time to involve the collective and involve your neighbours, because if you're adding any insulation, you want to wrap around as much of the thermal envelope as you can, and that might include your neighbour's wall or floor, etc. Finally, ventilation heat loss. So there's no method to calculate the air change rate. So the common name for the measurement or evaluation method is air tightness testing. Now, there's various methods for this. Personally, we prefer the low pressure pulse version because you can do room by room tests for more accurate data. And we all know that draft proofing is a method to reduce ventilation heat loss. And we'll move on to this topic real soon, but just to say here that overdraft proofing can lead to serious problems. So the important thing to take away with these three heat loss pathways is that changing one will affect the others. So for example, if you improve the planar U value of your ceiling, but not the wall, this will increase or make worse the psi value for the corner, which is the rate of heat loss through the junction between the wall and the ceiling. So improving all three heat loss pathways together at the same time, which we would refer to in the industry as a whole building or a whole house retrofit, is now the only logical way to move forward. So importantly, when addressing heat losses, you need to also be conscious of heat gains. Now, heat gains, much like heat losses, can be broken into three categories. We have metabolic, solar, and equipment. So metabolic heat gains are heat from our bodies, any warm-blooded animals in the building. Solar heat gains will be that comes from the sun through your window. And then we have various different equipment heat gains, which include cooking, lighting, fans and pumps, and latent gains from water heating, like the pipes that connect your boiler to your taps. We have direct and indirect equipment heat gains. So direct would be something like your oven whilst you're cooking, and indirect would be something like your fridge and freezer when it dumps out a lot of heat during its cooling cycles. So I want to apply this knowledge to a retrofit example, and I want to demonstrate the balancing between heat losses and heat gains. So here I'll be using the U value for heat losses and solar for heat gains, because typically solar is the only thing we can really have any effect on for existing buildings. So in this slide, I have the heat gain profile for the exact same tenement flat. Now, this is a retrofit assessment between two different window retrofit options. And all of this data comes from actual measured and monitored and calculated data that we at BRS have acquired over the years. So quite quickly, the pie chart on the left shows the heat gain profile for that flat and the total space heating demand for the flat if it were to have all the windows retrofitted with secondary glazing. The pie chart on the right is the heat profile for the exact same flat, but the windows were to be replaced by triple glaze systems. So both in this example, in this particular project, the secondary and triple glaze systems have the exact same U value. So they have the same heat loss value, which is 1.7 watts per meter squared Kelvin, if anyone's interested. And that is very low, by the way. It's very good value to get. The difference here is that the total solar energy transmittance, or we refer to a GT value, which is a measure of how much solar heat energy passes through the glazing and is used for calculating solar gains, those numbers were different. So whilst they had the same U value for heat loss, The secondary glazing system had a GT value of 0.76, and the triple glaze system had a value of 0.57. Now, this GT value is a ratio between 1 and 0, and the higher the value, the more solar energy you'll get from the sun. So for context, a single sheet of glass, say kind of 3 or 4 millimeters, that will have a GT value around 0.9. So the text above each of those charts shows the effect of the retrofit systems on the flat's total heat gains and the ultimate effect that on the flat's total space heating demand for the year. So the message here is that the selection of retrofit measures, it does demand special care and consideration. I've only used windows as an example here because windows tend to be the most sensitive to this special care and consideration. Retrofit specifications should never be seen as looking up the Argus catalog for the cheapest material or system. And when you're speaking with your designer or your retrofit installer professional, always bear in mind that heat loss or U values should not be the only metric by which you evaluate the retrofit options, especially for windows. So for example here, a good low U value will indeed reduce your heat losses, but you may not want to sacrifice solar heat gains to achieve those lower U values. And of course, cost comes into this as well, but we're just going to stick with physics for now. Now, I probably know what all of you are thinking. You're thinking that, okay, solar gains versus window heat losses, that's only really part of the picture. And you're probably experiencing this right now in your homes or buildings. And you're right. So this begs the question, what about overheating? So there was a simple calculation method that considered the building's heat losses and heat gains over the 3 summer months to predict the risk of internal temperatures going over the external temperature threshold. Now, much of that has been replaced with complex, expensive dynamic simulation modeling. And now we typically use the value of 25 degrees. If the building goes over 25 degrees for a period of time, then it's said to be experiencing overheating. But what does that mean for retrofit and retrofit projects? Well, it means that we should be focusing on the term thermal comfort as opposed to overheating. And you're well within your right as a homeowner or as an occupant to ask your retrofit construction professional for an overheating risk assessment or a thermal comfort assessment, which will include the assessment of the dwelling's internal surface temperatures. And this is where thermal mass starts to come into the topic. So for existing buildings, especially those constructed with mass masonry, they often get a bad reputation for being hard to heat. The better term is probably hard to keep warm. So if you have a building with high levels of thermal mass, that means it was constructed using mass masonry. That's going to be things like stone or concrete or concrete blocks. And these materials can act like a heat sink or a thermal sink, which means that the core of those elements, like a solid internal solid stone wall, can absorb large amounts of heat from the ambient air around them, which in turn will create, for a time, lower surface temperatures. And that wall, until the whole wall reaches the same temperature as the ambient air around it, that wall will feel cold. So this means that when you sit close to a mass masonry wall, specifically internal ones, that has a low surface temperature, that heat sink will absorb metabolic heat from your body much faster than most of the other objects in the room, like your fabrics and furnishings. And this often translates into feeling cold near that surface. Now, that accelerated heat transfer between your skin and a cold surface, it can happen at such a rate that most people can mistake that radiant thermal exchange as convective thermal exchange. So lower surface temperatures are very easily mistaken for being a draft. And then when someone feels a draft, what tends to happen? And out comes the draft proofing. Out comes the draft proofing foam, the tapes, the sprays, which is very dangerous. We're about to come on to that topic real soon. Now, I have a few metrics on screen here, which are typically used by the industry as key performance indicators of how the internal thermal comfort levels can be measured before and after retrofit to determine if indeed the space does feel uncomfortable. Also, after retrofit, or post-retrofit rather, be prepared to alter your heating's schedule, timer, and set points, etc. for your space heating system. That's there to help the surface temperatures and ambient air temperature to get into what we call better alignment. So after retrofit, it's often the case where you need to tweak your heating system to respond to the new thermal envelope that you've created. Now, this often translates into heating the home for longer at a lower temperature post-retrofit. So instead of short bursts of heat, you're now using lower bursts, lower set point temperatures for longer periods. Okay, so that's overheating and the importance of thermal comfort, but what about underheating? So I have to say that building physicists have always been deeply concerned about the detrimental impacts that fuel poverty has on a building's well-being, and often then the catastrophic and eventually fatal effects that fuel poverty has on the occupants. But I want to talk about unconscious underheating. So this comes down to building physics versus its cousin, building economics. I'm not an economist, but I do pay my energy bills, and that's the only qualification you need to understand this next part. So again, this data comes from a simplified version of what we had done recently with an Edinburgh tenement flat, mid-floor tenement flat in Edinburgh's Newtown. So let's say that it had a space heating demand of 15,000 kilowatt hours per year. That's pretty respectable for a building of this archetype. So that dwelling needs 15,000 kilowatt hours a year of thermal energy, of heat energy, to achieve A, the occupant's thermal comfort, and B, to keep the dwelling's thermal envelope healthy. So that means to keep the levels of relative humidity of the air down, and to keep the levels of surface temperature on the internal surfaces up. So let's say that this flat is gas heated, which it was, and let's just use a simplified tariff. So let's select 5 pence per kilowatt hour as the tariff. Now, to generate that 15,000 kilowatt hours per year, they were paying £750 a year. I've just ignored standing charges here for a moment. Now, if you're using pounds as the benchmark for building performance, and you're locked into trying to keep that space heating demand to a certain pounds per year, then the heating fuel tariff prices, when they increase, that significantly increases the risk of what we call unconscious underheating. So let's say in this example, you're used to paying around £750 a year to heat the home, and the tariff jumps from, again, for simple math, from 5p to 10p per kilowatt hour for the gas. But you're adamant that the house only needs £750 a year of heat to maintain healthy and comfortable conditions. This results in what we call unconscious underheating. So if someone is fixated on only spending £750 a year and the tariff doubles, then the amount of space heating that you're delivering to the home is effectively halved. Now, this translates into 3 things. First, and the most instantaneous and obvious, is that the occupants feel colder for longer. Next, levels of relative humidity take longer to drop because air temperature is lower. Not long after that, the surface temperatures are also lower for longer. And as we've just spoke about, the knee-jerk reaction to feeling colder surfaces, because you think that that feeling cold sensation is ventilation heat loss, the knee-jerk reaction is draft proofing. Now, it very well might be ventilation heat loss that's being experienced, but it's not guaranteed, especially if you've just started to feel cold after the tariff has went up and parts of the home that didn't feel cold previously. So what happens next? More draft proofing, obviously. Now, we have monitored far too many people locking off and closing mechanical ventilation extract fans, because when you've kind of already maxed out the draft proofing, you can get a little bit obsessed with finding that draft, which there may not be one to find. So what happens next? CO2, metabolic carbon dioxide levels start to rise, particulate matter 2.5 microns, those levels start to rise, and they'll continue to rise towards levels that are hazardous for health. Then what happens? Headaches, migraines, change in moods, drop in cognitive ability, skin and respiratory health issues. So the message here is twofold. First, never use pounds per month or pounds per year as an indication of how much space heating your building needs. It's much too sensitive to tariffs. Now, whilst we are all at the mercies of the energy gods in relation to tariff prices, we need to compensate our understanding of our indoor environments. So this means looking beyond air temperatures as a sole metric to define the thermal comfort of our homes. So what does that mean? So until tariff prices come back to some form of normality and market competitiveness takes away some of the burden for us, we must start to consider technologies like dehumidifiers and air purifiers if we're forced to, for the time being, unconsciously underheat our homes, or now consciously underheat our homes because it's just too expensive to run it. These two technologies, dehumidifiers and air purifiers, they are becoming essential to help with lower ambient air temperatures from our heating system, to help control levels of relative humidity and particular things like PM, particulate matter 2.5. Now that means you can use your extra blankets and warm clothing layers to keep your thermal comfort high, and then you can use dehumidifiers and air purifiers to manage the levels of relative humidity and indoor air pollutants that the indoor air temperature will be struggling to handle. Now, just a sense check warning. You've heard me saying manage and control relative humidity and particulate matter. The only thing that will remove levels of CO2 from your indoor environment is active ventilation. Now, whether that be wind-driven natural ventilation, or whether that be continuous mechanical ventilation, it may be necessary to de-retrofit some of the draft proofing to get those levels of air change rates back up to comfortable and healthy levels. But how do we know when we need to dehumidify our air, or to get an air purifier, or to have more or a different type of ventilation system? Well, that brings me nicely to the next section of this talk, which is water transfer and ventilation. So I want to start just to kind of demystify the process. There's a lot of myths going around about water vapor. I want to start with a few scientific facts. So water exists in two of its three forms, most commonly two of its three forms in our homes and in the materials that we've used to construct our homes. Now, these two forms are liquid water, which is oftentimes called moisture, and water vapor, which is also oftentimes called moisture. Every porous material in your home, for example, timber, brick, plasterboard, lath and plaster, stone, will have some level of liquid residing within its cells or its pores. Now, this is called the material's moisture content. And that moisture content, it will vary. Sometimes it will vary on an hourly basis. Sometimes it will vary on a monthly basis. But whether we like it or not, the levels of moisture content will vary in our building's material. Next, water vapor is often assumed to be only steam, like from boiling water, and that it only moves during times of high energy exchanges, like, for example, when the shower is on. Now, that's only partly correct. So what the water vapor I want to refer to this evening is both the high energy steam variety, but also the low energy water molecules that are always all around us. Now, these low energy varieties transfer due to differences in pressure across your building's internal and external surfaces. Now, that pressure difference on either side of your wall, for example, will partly dictate the transfer of water vapor through your building's thermal envelope. So just like temperature dictates the transfer and balancing of heat across your building's envelope, saturated and partial vapor pressures will dictate the transfer and balancing of water vapor. The last scientific fact worth mentioning here is that water vapor transfer observes the same principles as electricity and heat, meaning that it will prefer to follow the line of least resistance. So water vapor pressure differential, which is measured in kilopascals, does not naturally want to transfer through densities of materials that make up your wall, for example. The water vapor levels internally, they do want to balance with levels of water vapor externally, but it will prefer to do that via the line of least resistance. That typically means via the building's ventilation system or strategy or dehumidifier, which for us, that will mean that the typical ventilation strategy or ventilation system will mean the building's trickle vents in some windows or intermittent mechanical extract fans in our wet rooms. And then we open our doors and windows when necessary. So that particular system, that's natural or ventilation, that natural or passive ventilation system, that is the primary means by which water vapor internally will want to balance with water vapor externally. Now, what happens if we start to draft proof? First thing is that we lower the ventilation heat loss, which is a good thing, right? Well, not necessarily. So what happens when we draft proof some more past the point where it's healthy? Then we draft proof more again. Then we continue to feel that draft, which may or may not be there. So we start tampering with our extract fans, and we start draft proofing our internal doors, etc. Now that water vapor, that internal water vapor, it only has one route in order for it to balance with the external, and that is through the building's thermal envelope. And that is not a route that you want the internal water vapor to take. So this brings me on to the phase changes of water, specifically moving from vapor to liquid. So water vapor, like I say, does not want to undergo those kilopascal pressure changes that to get through a bunch of materials, but it will do if it has to. So for example, if the ventilation strategy or system has failed, or over retrofitting or over draft proofing has compromised the dwelling's ability to balance the levels of internal and external water vapor in the air, then water vapor will push its way through the walls and through the ceilings and through those joints and junctions in order to balance or harmonize with the external. It's going to happen whether we like it or not. But the important thing to note here is that the levels of water vapor will travel through your thermal envelope at different rates compared to how heat will travel through your building's thermal envelope. So if at any point in the heat and water vapor's journey through the wall, for example, from the inside to the outside, if the rate of those two differs significantly, and now by significantly, I mean the rate of heat transfer is faster than the rate of water vapor transfer, then the water vapor will condense into liquid water. Now, if that happens on the very first layer of your thermal envelope, so for example, your lath and plaster internal surface of the wall, that is what we would refer to as surface condensation. If that condensation happens somewhere between the wall's internal and external surface, that is what we call interstitial condensation. So what does all of that mean? So for retrofit project, or retrofit materials rather, you often hear the word breathable, meaning that a so-called breathable material can handle the water vapor transfer from vapor to liquid. So it can handle condensation in your wall, for example. Firstly, your wall or your ceiling or wherever should never be expected to handle large amounts of condensation. Secondly, breathable is not a scientific term and it cannot be measured. Breathable is actually a combination of three water transfer properties: hygroscopicity, cell structure, and permeability. These are kind of words to hang on to when you're speaking to your construction professional or your retrofit advisor. Lastly, be careful of any construction professional that will immediately disregard a certain material or a retrofit position of that material without first understanding the hydrothermal dynamics and the ventilation strategy of your exact home, as this can greatly influence the success of any retrofit material that is chosen, paid for, and installed. A perfect example of this would be material like phenolic foam insulation or polyurethane or polystyrene that could be installed either in front of your lath and plaster on the inside or put behind your lath and plaster to fill the air layer that might be in your wall, for example. Now, I've monitored walls like this for over a decade, and certain conditions, those materials were perfectly fine, nothing bad happened. In other conditions, it wasn't good. But why? Why do some materials in some walls work fine in some dwellings, but other material, the same material, may not work so well in a similar dwelling in a different situation? Now, in most instances, it comes down to, firstly, the levels of moisture content in the pre-retrofit wall, for example. And then it also comes down to aggressive draft proofing with no consideration for the post-retrofit ventilation system. So the message I want to leave you with here is there are two types of ventilation, and both types will be summed up to equal the total amount of ventilation heat loss. Now, the first type is what we in the industry call unregulated ventilation. Now, that is probably the closest thing to what most people will refer to as a draft. Now, these drafts or these unregulated ventilation pathways, these are where air movement pathways that you cannot regulate. So you can't switch it off. There's no lever or there's no mechanism for you to turn off that ventilation pathway. These are things like drafts around poorly fitted windows, poorly sealed chimneys, pipes, ductwork, and other penetrations through the building's thermal envelope. Now, the second type of ventilation is what we refer to as regulated ventilation. Now, this means the amount of air that travels from the internal to the external through the building's actual ventilation system, which is designed to be there. Now, if you are in a tenement flat in Edinburgh, for example, then your ventilation system is going to be something like intermittent extract fans in the wet rooms, and at times you open and close your windows and doors to balance the water vapor across the surfaces. Now, the thing to bear in mind is there will always be a necessary heat loss penalty to properly ventilate your home. But unregulated heat loss pathways, around dodgy windows and around pipes, etc., they are not and should not be considered part of the building's ventilation system for maintaining good indoor air quality. It's your building's regulated ventilation system that should be considered. So the takeaway message here is never rush to retrofit, no matter how tempting or under pressure you are to change the thermal envelope. Stop, think, and listen to the building. So it is essential to make sure that your building is actually ready to retrofit before you're doing anything. And a trusted, experienced construction professional seasoned in the science of retrofit and building performance evaluation can help take you through those steps. But please don't trust a construction professional that says something like, yeah, we don't need to do any pre-retrofit measurements. We have worked on or we have installed on buildings like this for years. In that situation, my response typically is, sure, maybe, but have you actually worked on this exact house? Like, do you know the exact moisture content of the stone in this wall during the winter period? Do you know the exact ventilation pathways of this exact dwelling? Because if the answer is no, then they do need to be doing pre-retrofit measurements for baselining. But that's what the professional should be doing. What can you do to inform your decisions and to give you the power over decision-making for thermal retrofit projects? Well, as is almost always the case, knowledge will give you that power. And the knowledge typically comes from the data. So now I want to move on, to wrap up this talk to talk about the types of data that you can get and your construction professional can more readily get to better inform any retrofit decisions. Now here I want to very quickly cover the cheap and cheerful hardware that you can use along with the scientifically calibrated hardware that you should expect your industry professional to come in with. So the terms we'll be using here again are pre and post retrofit, and that just again simply means before and after any thermal insulating material is added. So we use the term measure to capture a single point in time value. So that'd be like an IR camera or moisture content meter. And we use the term monitor to capture values over time, like temperature, relative humidity, internal thermal comfort conditions, etc. But why measure? Why go through the whole rigmarole of getting data? Well, first, the pre-retrofit data gives you and your construction professional a baseline for the hydrothermal and ventilation performance of your building, which acts as a benchmark that the construction professional can use to calibrate digital models of your building, which is used to shortlist a selection of retrofit measures and which greatly assists with the specification of the optimal retrofit solution. And this whole process is what we call de-risking the retrofit process. Secondly, the post-retrofit data gives you values to compare to the baseline or pre-retrofit values. And this will let you quantify the impacts of the money that you've spent, but also these data sets can provide you with vital kind of canary in the mine shaft type of insights. Now, it'll let you see as early as reasonably practicable if something untoward is happening. So after retrofit, it will take some time for those sub-environments within your internal environment to adjust to the changes that have been made to the building's thermal envelope. So if something bad is happening post-retrofit, you want to detect that as early as possible so you can get that before too much damage has been done. So how do we measure? So lots of hardware is typically the answer. Some of that hardware is cheap and cheerful and super intuitive, and some is very expensive and requires specific training and deeper knowledge of building physics and apparatus. Now, for the purpose of the time, I know we're at the 8 o'clock mark. I don't want to go through all the processes and all the costs of this equipment, but I do want to simply say that there is low-cost equipment and free to access citizen scientist type websites that allow you to start to measure the baseline of your existing building. And these are on the left of the screen there. Now, you can pair your energy bill data with like weather adjusted information from the likes of Wonder Map, and that will give you a very good start as a baseline for your pre-retrofit and understand the impacts post-retrofit. Whereas your construction professional can provide even more intel using more expensive equipment, which I've shown here on the right-hand side of the page. And I've just labeled these so you know that it is possible to measure these things. So there are equipment, it's not new, it's not innovative, it's not expensive. From a construction professional perspective, it's not expensive for them to bring in some of this hardware to help alleviate some of your concerns or some of the risks. So the take-home message for this section, again, are do not rush to retrofit. Get the data, create a baseline, satisfy yourself that you're investing in the right retrofit measures. Make sure that the building is ready to retrofit. This could mean removing some of the earlier retrofit works or repairing and restoring something before any new material is added. Carrying out maintenance and repairs is often a very essential first step before you retrofit anything. Don't be afraid of the data. And if you are uncertain of the data, do find a construction professional with retrofit experience and building physics knowledge to talk you through what that data means, which then brings me nicely to the final section of our talk, which is whole house or whole building energy efficiency retrofit. Now here, I'm going to very briefly set out the location of and the types of thermal retrofit materials or measures rather, that we can add to our existing buildings. And importantly, the things that you should be aware of when considering some of these measures. Now what you're about to see is not an exhaustive list, neither is it a list of specific products or brands. It's down to your research or down to your construction professional to do that research to make sure the right brand or product is being selected. Also, I'm not one of those construction professionals that likes to make the retrofit process measure-centric. meaning we would choose a specific retrofit material before understanding the building. So I, like the best of us out there, we like to start with what we call an archetype-centric approach, which means we get data from the building, which will tell us what materials we can rule out, what locations we can rule out, and then the optimal material and location to install in that building. But for the interest of time, and because I don't want to go into specifics too far, I'm going to keep the advice here just a little bit generic than I otherwise would like to. So last couple of slides, let's start with, as many of us do, with draft proofing. So things to be aware of. For pre-retrofit, do you currently experience overheating in the summer? If so, then post-retrofit, those levels could get worse. What are the pre-retrofit air change rates? Are they just above adequate? If so, post-retrofit, those levels of air change rates are very likely to drop and get worse. That means that the post-retrofit air change rate could compromise certain retrofit measures. For example, indoor wall insulation and secondary glazing can be particularly sensitive whenever the air change rate drops below adequate levels. So you do want to see results from a pre and post air permeability test to see two things. First of all, to see that what you've paid for has indeed reduced the ventilation heat loss from the unregulated ventilation pathways. But the second thing you're looking for is that the air change rates have not reduced the hazardous levels for either you or the building. Now, for ventilation systems, you have your passive natural ventilation, which is pressure driven by the wind. So it's very dependent on if the wind is blowing, how fast it's blowing, and where it's coming from. That particular system may not be sufficient to deliver adequate air change rates post-retrofit, which means that the building is in danger of being over-retrofitted. Now, the solution here is to either de-retrofit to increase those unregulated ventilation pathways, which is not always advisable, or change the ventilation system to an energy-efficient continuous mechanical ventilation system that you can regulate and you can control. For walls, we have three insulation types, or think of them as three locations. We have internal, cavity, and external wall insulations. So internal wall insulation, things to be aware of. The ventilation strategy, like I've just said, be aware of the ventilation strategy for the house. Is it adequate pre-retrofit? Is the ventilation adequate pre-retrofit? Would too much draft proofing post-retrofit reduce air change rates to a point where water vapor is forced to transfer through the insulation? If so, you may be looking at instances of surface or interstitial condensation. Cavity wall insulation. Is the cavity actually ventilated? Meaning the air in the cavity is connected to the external environment. Like actually connected, meaning actual air movement, not just like a hole in the wall that is facing the outside. If so, then that air movement could be serving a particular purpose, and then filling that cavity could be a very bad idea because you're preventing that air movement to do what it was doing. External wall insulation. Now, I know this isn't particularly applicable to the historic archetype, but I'm going to cover it here just for completeness. The continuity of the thermal envelope is vitally important. Now, this is why EWI is so common for certain archetypes. So for EWI, it is essential that the installer removes everything on the external surface. Now, I mean everything. Alarm systems, downpipes, lights, absolutely everything. For all wall insulation types, do make sure that the designer, and by extension, the contractor, addresses those thermal bridges. That's those junctions around your corners and your edges. Now, what you do want to see is those IR thermal images pre and post, and you really want to see those temperature factor values for those thermal bridging locations, because remember, temperature factors are a vital assessment of the risk of surface condensation, and they can be both calculated and measured. Doors, very quickly, solid doors, things to be aware of. Whenever you're insulating the inside surface, which is typically the place door insulation is added, things like letter boxes, hinges, door locks, and the swing can be compromised. For doors that are wholly or partly glazed, make sure the window gets considered. And secondary glazing is pretty much a good application of the technology to doors, glazed doors as well as windows. As for windows, things to be aware of for all windows, if you can and you want to replace the window, then do be aware of that relationship between heat losses, which is the U value, and heat gains, which we spoke about earlier. If the window is worth keeping or keeping it as non-negotiable, then repair and restore as much of the original window frame and the mechanisms as possible. For glazing, things to be aware of, you want to decide if you want to improve just the glass. So that would be using things like low emissivity film or thin stick-on polycarbonate double glazing on each pane of glass, or if you want to treat the whole opening with comprehensive secondary glazing. So for any system, be aware that you'll need to clean and maintain those windows at some point. So treating the whole window, for example, that comprehensive secondary glazing, that will improve the U value of the entire opening, which includes the glass, the frame, and any unwanted, unregulated ventilation heat loss pathways where your pane, your glass-only solutions will not. Right, so roof, things to be aware of. You want the insulation laid above and between the joists. So watch for the compression of any attic floor systems, and do inspect the insulation after any work has been done in the attic. So for example, any electrical, plumbing, or TV aerial work has been done. In the coombe, do not allow the ventilation pathway from the eaves, which is where the roof guttering will be, into the attic to become fully blocked or filled. For the rafter, which is a diagonal part of your roof, if you have insulation going into there, be aware of the water vapor resistance of any materials up there. So for example, bituminous felt that might be under your slates or tiles, so that will affect the material's performance when you put it up there. For floors, things to be aware of, any floor, be aware of the composition. It is common for pre-1970 buildings to have some timber suspended floor in some parts, then flagstone or concrete in the wet rooms like bathrooms and kitchens. For solid floors, if you have to add insulation to the surface, be aware of any changes in height. That will affect things like staircases and doors and things like that. And for suspended floors, insulating between the joists under the floorboards tends to be the only solution here, and they can be quite troublesome and costly. Right, last two slides. So post-retrofit evaluation. So you have your pre-data, something's been installed, now you're doing your post-data. What are you looking for? Well, when you get your post-retrofit data and you're comparing it to the pre-retrofit data, increases in anything is typically bad. So increases in ambient, somewhere ambient internal air temperatures, bad. Increases in internal relative humidity above 70% RH for long periods, bad. Internal CO2 above 1,000, 1,500, 1,000 to 1,500 parts per million for prolonged periods, that's bad. Internal particulate matter 2.5 levels for prolonged periods, that's bad. Water heating systems, winter heating, space heating fuel, if that increases during your winter period, your energy bills increase, that's bad. So make sure that whatever data you're comparing is weather normalized for the year that you're comparing, so you can do that safe comparison between the years. And that's something you're interested in, then your construction professional can help with that. Very last slide. The final message for all of this, the kind of big take-home messages. If you are in flatted accommodation or flatted dwellings, then they can be more challenging for a thermal retrofit. Specifically because your dwelling's thermal envelope will most likely include a wall and or floor and or a ceiling that is part of your neighbor's thermal envelope. So when you're adding insulation to your own thermal envelope, you do want to have that whole building solution, which includes those junctions and joints, so those thermal bridging points that we spoke about earlier. So this is typically the time to involve the collective and to have those discussions with your neighbors to see what the most cost-effective method is. Be aware of any construction professional that resists pre and post retrofit monitoring. And be aware of any construction professional that says, we don't need to measure anything. We know all there needs to be known about sandstone walls. Yeah, they may know the theoretical performance of sandstone, for example, but they need to know the specific hydrothermal performance and ventilation pathways of your home before anyone starts to add any insulation to any location. Now, you might be told that it'll cost you money and time to do a proper retrofit building performance evaluation. Now, it doesn't cost that much in the grand scheme of things, but it will cost time. Some of those measurements and monitoring we spoke about, they can only be done over the winter period or over the summer period. So it will cost you time, but ultimately, thinking about the amount of time, the amount of money you're putting into the whole process, can you really afford to get the retrofit wrong? Especially with so many low-cost monitoring options out there that can help de-risk the process before investing something that cost thousands and tens of thousands to put right. Finally, and we have not touched on the wider environmental impacts at all, but just to give the last word to holistic sustainability retrofit. If your personal priorities also include environmental impacts and whole life cycle sustainability credential of the materials that you're investing in, like the embodied energy, again, you are well within your rights to ask your chosen retrofit professional for an EPD. Now, an EPD is an environmental product declaration. Now, these EPDs will tell you just how much of an impact that material has had on the environment to get to your building. Now, these EPDs aren't new, and any decent professional can talk you through what the numbers on those EPDs mean. And if that is something that you're overly concerned about, then that is something that you can have actionable intelligence on to help better specify what materials you're choosing, say between synthetic materials and your natural biogenic materials. So I want to leave it there. Apologies for going over. I know it's now 8:15. So thank you all for listening. I do hope that some of that was valuable and that you picked up some useful tips.